We learned in the previous section that the torque net is equal to 0 when there is no change in angular motion or the angular acceleration is 0. So we summed our torques and set them equal to 0. But what happens if when you sum your torques it doesn't equal 0, like we talked about in the first example problem in this chapter? That would mean that there is an angular acceleration. Before, though, we can discuss how we actually get between torque and angular acceleration, we have to introduce a new concept, and that is called the mode of inertia. So if you've ever been responsible for loading a top-loading washing machine with an agitator inside, and you've been inexperienced with it and you shove a blanket all on one side of the agitator and don't evenly distribute it, you get a scenario where the washing machine starts shaking back and forth and vibrating, and it's not a good thing. However, you take that same blanket and neatly wrap it around the agitator so that the load is balanced, the washing machine runs smoothly. So it matters how the mass is distributed in the system when it is rotating. And how we characterize that distribution of mass we're going to refer to as the mode of inertia. So mode of inertia is how mass is distributed in a system that is rotating relative to the rotation point. All right. Now, the tricky part about mode of inertia is that it depends upon what mass is actually rotating, or the shape of what is rotating in the system. So if you go to the constants table link in Blackboard, there is a link to mode of inertia equations, and this is something you would be provided on an exam. There is one mode of inertia equation that is actually on your equation sheet, and that is the mode of inertia of a point mass. And that is mr squared. And a point mass is a small mass that is rotating about a rotation. So if you have a point of rotation and you have a mass that is rotating around, and of course I didn't draw the rotation point in the center, that would be a point mass. This is going to be different than something we're going to characterize as a sphere, which is like the Earth rotating about its own axis. So in this case, m is the mass of the point mass, and r is the distance from the rotation point. And when we calculate the mode of inertia of a system, it's going to equal the sum of all the individual mode of inertias of anything that is rotating in the system. So let's talk about an example here. So let's pretend that we have a solid sphere. So we have a sphere and it's filled in and it's rotating about its center. And I attach 2 point masses, one over here and one over here. So if I want to know the moment of inertia of the system, I have to add together the moment of inertia of point mass 1 plus the moment of inertia of the solid sphere plus the moment of inertia of point mass 2. So we know what the moment of inertia equation is for a point mass. And so this would be R1 here, and then mass 1. And then we need to look up the moment of inertia equation for a solid sphere. So I'm looking over here at my mode of inertia equations that are linked in Blackboard. And solid sphere is 2/5 mr squared. And the r in this case is the radius of the sphere. Then we need to add in mr squared again for the second point mass. So this would be R2, and then this would be mass 2. And if I had given you values, you could then plug in the values and solve for the mode of inertia of the system. So whenever you do a problem where you ask to find mode of inertia of the system, you need to first establish what shapes are rotating in the system, then look up what their mode of inertia equations are individually, then you can add them together, and then plug numbers in and solve for the mode of inertia. So there are several steps of this process because the equation is going to look slightly different depending upon what shapes are rotating in the system. Alright, now that we know what mode of inertia is, we can learn the other half of the equation for torque. So the torque net is going to equal the mode of inertia of the system times the net angular acceleration. Now it's very important, and of course these both equations are on your equation sheet, to remember that the torque net equals the mode of inertia of the system times the angular acceleration. But torque net still equals the sum of the individual torques, or F1 R1 plus F2 R2 plus however many forces and thus torques are applied in the system. So you have to keep in mind that these are two halves of the same equation, where you can actually set these two equations equal to each other. So if you're given a force and a radius, and the shape that you can look up what the mode of inertia equation is, you can solve for angular acceleration. So you have to remember that there are two ways of solving for torque and that you can equate them for each other.